Hello, this presentation is about flow map layout. This paper is written by Gautam Fan, Ling Xiao, Ron Ye, Pat Hanaram and Terry Vinograd. This paper is all about flow map development. Maps used to show movement of an object from one place to another are known as flow maps. Flow maps are usually developed using hands, but in this paper they attempt to show a method of hierarchical clustering to create trees given a certain input in the form of nodes, their position and flow data. Visual clutter has always been a serious problem in visualization of flow and topology. Flow maps are able to solve this problem. Lines of varying width reflect flow. Clutter is reduced if we join streams on the same direction. Using hierarchical clustering, a connection between the root and the leaves are help create a tree. Hand-drawn maps have always had some significant better advantages such as intelligent distortion of position, merging edges and smart edge routing. Clusters are modeled as rectangular boxes enclosing their nodes. Edges check for intersection with boundary boxes. To replicate these characteristics, the following design is used for their system. We can see the input parameters, the nodes, positions and flow data. Then we apply layout adjustment, primary clustering, rooted clustering, spatial layout, edge routing and rendering. Layout adjustment. It ensures a minimum vertical and horizontal separation. It uses the 4-scan algorithm and the complexity is big O of n square. Nodes are sorted into two lists, one ordered by the x coordinate and the other by the y coordinate. The algorithm also consists of a horizontal scan followed by the vertical scan. The authors tried to use the directed method algorithm, but there were issues with the node positions. The flow maps with stable node positions for a given set of nodes is preferred. The force directed technique resulted in slightly different layouts each time because of the randomness in the algorithm. Primary hierarchical clustering. Using agglomerative hierarchical clustering, binary trees are produced. Input nodes are leaves from the clustering. The distance between the clusters is the Euclidean distance between the centers of the rectangular boxes. Rooted hierarchical clustering. The tree produced by the primary hierarchical clustering is not suitable because its root is a combination of clusters of input nodes. For a given root node R, we accumulate the nodes to be reclustered by following parent pointers from node R of the root of the primary clustering P. This is a modification of the primary clustering. It takes big O of m squared time, where m is the total number of nodes in the system including the nodes generated by the primary cluster and input. The way the nodes are merged are different for rooted and primary. Without reuse of the substructure, they are able to implement this whole algorithm in big O of m squared time. Spatial layout. Each node creates a branching structure from the parent to its two children. The challenge here is to minimize the crossings, the edge crossings. Here is an example of the spatial layout. 3 examples to be specific, where 2 leaf nodes are there, 1 leaf node, 1 cluster and 2 clusters. Each of them are different and so they are being handled in different ways using recursive calls or real edges. Edge routing. Route edges around boundary boxes is the main aim of this step. There is, however, a consequence. Edges from the root node to its immediate children are not rooted. Here is another example of what edge routing looks like. we are trying to route two edges B1 and B3, but they tend to intersect a cluster C1. Here they show you what is the best way to choose the closest corner. If the area of A is less than the area of B, then corner P1 is chosen, else corner P2. In this situation, we have to create a new node to avoid C1. But sometimes even after creating a new node, we are not able to avoid C1, and hence we have to move the B3 node. Multi-layer issues. Each new query might introduce new nodes. We need to assign all nodes their initial position before we begin. After assigning the position, we run the layout adjustment algorithm. If we get new nodes, we run the hierarchical clustering. Each cluster has a list of layers with which it is associated. Rendering. Each edge is a Catmull-Rom spline. Width is regulated based on display options. It uses linear and/or the logarithmic functions to be able to display the flow data into these visual splines. The legend is created by k-means clustering. The legend tends to have 7 categories, but it is not necessary to have 7 categories in each visualization. Each and every binary branch, there is a starting point, and that starting point is shifted by a proportional distance based on the child width. Let us discuss the results of this paper. The paper claims to show aesthetically pleasing maps for a variety of datasets, and it only takes a few seconds to run. Intelligent distortion. Relative positions are preserved by the four-scan algorithm. There are still a possibility of distortion in their maps. Merging of edge shared destinations can be achieved by hierarchical clustering to find spatial clusters. All tree splits are binary, but this can lead to a problem if there are too many splits in a small area that can create too many nodes and clusters. That again leads to clutter. Intelligent edge routing. Flow maps work mostly well for simpler data, but sometimes do not work well for larger data cases. Edge crossings tend to happen more often. Layering and branching substructure. Maps work well for sharing substructures across flow maps that share a common set of nodes. Using a log functions to map data for data sets which have higher magnitude, and linear functions work better for lesser magnitude data. Now here are some examples of how the flow maps actually look like when you implement this system. To make a side-by-side comparison, this is a computer-generated flow map for the migration data from California between 1995 and 2000. Notice the clutter. The same map is produced with this system, and the flow map looks brilliant, as it is very easy to distinguish which streams have more data. Here's another example to show the close-up imports of Spain and France. Thank you for watching.